Welcome everyone to episode 2 of the Pelmerex series.
I'll take on this slide, Dave. So just for those of you who haven't been with Silicon Halton before, been to a Silicon Halton event. I mean, Silicon Halton launched just over a decade ago now. And our mission has been to, connect people and technology so we can all learn, the mantra, the rising tide raises all boats. And that's what we do. So we have various events happening throughout the months, throughout the weeks, continuing through the pandemic. Obviously, everything virtual now, to help us all just get better at what we do. And then I'll finish off with this slide too, Dave. We're, virtually all volunteers taking on some small task to showcase a little bit of what we can do for the good of the community. If there's something you'd like to add to Silicon Halton, like Yogi mentioned, he's, running, started an ERP peer-to-peer software seminar series. And that's just, him taking his expertise and sharing it with the community. And so those opportunities are available, for the betterment of everyone. And I'd be remiss if if we didn't say thanks to all our sponsors that help, fuel the back end of the company to, pay for our accountancy fees and hosting, et cetera, et cetera. So thanks to this group of companies. And then the last slide for you, Dave.
All right, driving accuracy in our weather forecasts with technology. Well, I'm looking forward to hearing about this. So I'll send it over to Ian now.
Mind if I jump in, Ian, quickly and just kind of chat about
go ahead, yeah.
What Pelmerex is while you're loading up?
Yeah.
Cool, awesome. So, Rick and Dave are really saying thanks to Matt and Ian for doing this tonight. It's really Ian. Ian's put some great effort into this, and I know he's going to do a great job because he's awesome at what he does. But I just wanted to quickly kind of tell everyone and remind everyone, in case you don't know who Pelmerex is, this is going to be brief, but really, Pelmerex is a 31-year-old company. We're located, our headquarters are in Oakville, so that's why we're part of the Silicon Halton meetups going on here. We also have offices in Montreal, Toronto, Madrid, and oh my gosh, we just acquired a company recently in the States, and I can't remember where they are. That's how.
Salem, New Hampshire.
Boston.
Salem, New Hampshire. Thank you.
Oh.
Thank you. Yes. So, and what we do, you'll know our bigger brands in Canada are really the Weather Network and Meteorological. So we are doing weather forecasting and driving and delivering weather data to our consumers. We have a very large Canadian focus, but we continue to expand that throughout the world. In Spain, we're the #1 weather provider with El Tiempo. And as well, we also work in different divisions. We have a data division, we have an ad services division, and really, it just keeps growing. So that's all I'm going to say about what Pelmerex is and who Pelmerex is. I'm going to turn it over to Ian now, who is really going to tell us about the really cool stuff that he and his team do here at Pelmerex, the Weather Network.
Okay, so thanks, Matt and Dave and Rick for the introductions. It's my first time presenting at Silicon Halton. I have a very much a science focus in my role at Pelmerex, so appreciate that's not everyone's forte, but I'll try not to send you all to sleep too early this evening. In the first session of the series, Matt and some of my other colleagues and technology leaders, they provided a good context overview of our technology, how we develop it and use it at the company. What I want to do this evening, though, is really a couple of different things. I want to provide some good insight into the weather data that we use, how we process the data, and in order to provide value to end users, our customers. In weather products, sort of general statement, the customer value really lies in how useful the product is in helping the customer make a decision. And these decisions can be about their personal lives, work or business activities. So it's really in how good the information is to help them make their decisions. Okay, so In the agenda, two main areas, as I said. First, where our data comes from, some detail about the different types of weather data. I won't read the whole agenda, you can see that for yourselves. The second part will be on the way we leverage research and development activities, software engineering, etc., into turning this the data into useful information in products. And I'll give you some examples of exactly how we do that. I'm hoping there'll be plenty of time for questions as well. I don't mind how the questions are done. If you want to stop me midstream, that's okay, or wait until the end. It's entirely your decision. Okay, so quick overview of who we are. This is the Meteorology Research and Development Team. Everybody's on the call tonight, I think. I'm Ian, of course, director of the team, Met R&D. We have Jan Lee as well. Jan came to us with a PhD in atmospheric science from the University of Utah in the US, and also York University in Toronto, where he worked on a project, a collaborative research project with Palmrex a few years ago. Jan brings significant expertise in something called numerical weather prediction, which I'll explain some details of. Prashamsa is also a PhD in satellite meteorology, originally from Nepal, been to Japan, Hawaii, and now Canada. She brings significant expertise in satellite meteorology. Brian Bernardi is also here. He's Met Systems. He looks after configuration and administration of different development applications for weather forecasting. And our team mandate is to identify new and investigate enhancements to existing data that's used for the weather information products at Palmrex. Just like to start with this slide, which might seem a little bit strange. It's a famous quote, actually, by a statistician, not a meteorologist, nothing actually to do with weather data directly. But this guy Deming was, some of you might have heard of him. He was a famous statistician, and in post World War II, in the years after World War II, he was a pioneer of total quality management. He was actually recognized by the Japanese government for being probably the single biggest influence on the recovery of the Japanese economy after World War II. It's really relevant to weather applications, though, his quote. I really like it. It's very poignant. There's no magic in weather data, weather information. All there is data and how it's processed into information. So, and it's a nice sort of springboard for getting things started this evening. Okay, this is some of the governance behind weather data. We have an organization called the World Meteorological Organization. They provide coordination and policy oversight for exchange of meteorological data globally. Their origins actually date all the way back to the 19th century. They started out as the International Meteorological Organization. I believe that there was a conference in Vienna in about 1870 something, where they sort of got started. They became in the first part of the 20th century, their focus was primarily on shipping interests, because that was the way people moved around the planet back then. After World War II, when aviation really got going, it was aviation that really drove a lot of the requirements for weather information. And the WMO actually became an agency of the United Nations around 1950. The WMO is pivotal in that they ensure that data is shared between all countries for the greater good. We're talking about free data exchange. The data is just completely freely shared. That's not to say you don't have to pay for data sometimes, but without this free data exchange, there would be no such thing as weather services. Data is shared between countries because the weather simply doesn't recognize any national borders between countries. Events in one part of the world can and do actually affect regions in other parts of the world in very complex ways. So without the WMO, the coordination of international data exchange would not exist, and therefore weather information services could not exist. The technical background that they use is, and they put in place actually, and they create the framework for, is something called the Global Telecommunication System. It's GTS for short. It's quite well known in weather services, obviously. It's got 3 layers. The main layer actually has 3 collecting centers for weather data. There's one in Washington in the US, the other one is in another one in Moscow in Russia, and the third one is in Melbourne in Australia. And I think the main takeaway from here is that data is the fuel for weather applications, and the WMO enables the global data exchange. Okay, different data types. Most of the weather data that we use actually comes from traditional sources within WMO's data exchange framework. That's probably not too surprising given what I've just said about the importance of WMO. All of the data types from the global observing system you can see on the left-hand side there are received at Pelmorex. Many of them would not be used, but they are all received in our building. Some of them are much more heavily used than others. Data types that we make intensive use of from that slide would be observations from weather stations and also ground-based weather radar. Data from weather satellites is probably the most voluminous data that's used or that's available. It's used at Pelmorex for weather event analysis and diagnosis, and we're actually working toward the direct use of satellite data automatically in our current weather conditions products. NWP stands for Numerical Weather Prediction, that uses complex computer programs which encapsulate the different, well, varied and very different physical processes and physical properties of the atmosphere. There are multiple NWP data sets available, and we make heavy use of them because our product emphasis is on weather forecasting. NWP data actually comes from government-funded centres, like the Canadian Meteorological Centre in Montreal, the National Centres for Environmental Prediction, which is part of the US National Weather Service. They're based in Washington. And the European Centre for Medium Range Weather Forecasts, which is currently based in the UK, but being a European organization, they can be based anywhere in Europe. In fact, they're moving to northern Italy next year. They're co-funded by about 20 or 25 different governments across Europe. For the actual data acquisition, we use dedicated satellite receiver systems, as well as IP methods like FTP and HTTP. As you can probably imagine, the management of all of this data itself is quite complex. We have a lot of monitoring to do to ensure the availability of the data. And we need to make sure that we have data redundancy to ensure the uptime of various data processing systems that we have running at the company. Now, a third type of sort of main category of weather data is becoming more prevalent as a result of IoT, Internet of Things. We refer to it as non-traditional weather data, or NTW data. So on the bottom right-hand side there, it includes observations from personal weather stations, which are owned by general members of the public. Any of us can own them and put them on the side of our house and get observations from them, put them on the internet, and they become available through different agencies. Observations can be generated from vehicles as well, from different readings that they have. And also we can get some observations derived from closed circuit TV images. Now, some of these non-traditional weather observations are used in our operational data processing, but for the most part, they're only used in research projects at the moment. And I think that's probably generally true. I think most weather providers, although they would have tried using non-traditional weather data, for the most part, it's a research activity. Okay, so numerical weather prediction. It's become the basis for weather forecasting generally. And when I started as a weather forecaster more than 30 years ago, NWP was around, but it really didn't have a significant role to play in how we produce weather forecasts. Now it's absolutely central. It's the most important data set that we need to produce weather forecasts. NWP is the generic term given to weather forecasts made by computers end to end. So the NWP software itself encapsulates the mathematical equations that have gradually evolved over many years of, many decades actually, of scientific research. The equations represent the physical processes of weather, things like cloud formation processes, rain and snow, and ultimately the storms that develop as the weather evolves. The original concept of NWP actually came from Lewis Fry Richardson. This is the guy on the left-hand side. He was a British polymath. He was a mathematician, physicist, meteorologist. I think he was also a psychiatrist or something like that, or a psychologist. So he's one of those, in those days, scientists did a bit of everything. Richardson's idea was to calculate the weather using equations that he had developed during World War I, actually in between his shifts on the Western Front as an ambulance driver, believe it or not. In fact, Richardson computed a 6-hour weather forecast by hand, which took him 6 weeks to complete. But of course, he was ahead of his time. He needed computers to do the work faster than the weather actually changed. And when computers eventually became available, decades later, the theoretical concepts that he had actually developed himself were incorporated into the early models. Richardson's dream was a forecast factory. He imagined a sort of a spherical concert hall, something like on the right-hand side. And in this spherical hall or forecast factory, as he called it, there would be human calculators, each of them responsible for a small geography. And then in the end, all of these different calculations would come together to produce the weather forecast. Richardson actually estimated that 64,000 people would be needed to compute the weather at the pace that it evolved, which is pretty broad thinking really for the time. Coincidentally, the fastest computer in June 2005 was the IBM Blue Gene L. That computer had 65,000 processors, so he was quite a visionary. Okay, so here's a quick glance at what a modern NWP system might look like if you were able to view it in such a way. Of course, you can't. It doesn't. This is a schematic, and you can see there's the Earth, and it's carved up into discrete grid cells in 3 dimensions. We have the horizontal grid on latitude, longitude, and there's also a vertical grid that extends right through the atmosphere. It covers the whole globe, and each individual grid cell represents some physical process that has been researched and understood, and mathematical formulas have been developed to represent it within the model. It includes things like clouds and precipitation, various momentum and energy exchanges between the oceans and the atmosphere. Okay, so the different weather information products that we have. We have on a timeline anything from recent weather, recent past weather, through current weather, a few hours into the future, and then forecasts out to several days. In fact, I think the longest range forecast we currently do normally is around 2 weeks. There is actually a product that we also have which represents monthly to seasonal forecasts. I'm not showing it here. I'll touch on it a little bit later just to give a flavor of where weather information products are headed in the future. The process that we use at Palmer-X is, it begins with a strategic decision to work on a project which we think that will substantially or substantively improve the existing weather data sets. Once the data is integrated into production, it will subsequently improve the quality of information to our customers. That's pretty well validated before we even begin the research. We have a good sense of which areas of our infrastructure need to be improved. And so we have a pretty good sense of which projects we need to work on. But once we get into a project, we start with acquisition of data. We research and design algorithms to make the best use of the data. That's typically our group. And it all culminates with a product build in our production environment to benefit our customers. This is a very high level, quite idealized process, but it's It's not linear. It's very iterative, and it can get quite complicated depending on the product need. Okay. So the first type of product I'd like to talk about is something that we utilize a process called gap filling. Near-term weather conditions do matter a lot for all of our customers. So we've done internal research on this, and we've also done a lot of collaborative research, excuse me, with university researchers. I mentioned Jan Lee, who is in our group at the moment, but he was part of York University. He was a postdoc there, and he worked with us on a project to improve our current conditions. We've done significant software development to support the product, and we continue to support and maintain the technology going forward. So the current weather condition problem is, how do you fill gaps in a sparse network of weather stations? We get observations from about 6,000 weather stations around the world each hour. And the system that does the gap filling we call virtual observations, and it expands this out to more than 100,000 locations currently. The map on the left illustrates the sort of problem I'm talking about, where in Ireland there's a relatively sparse number of data points. They're coming from typically from physical weather stations. But the densification over the UK is the result of the gap filling that's part of our virtual observation systems. The solution, which is a schematic on the right-hand side, which roughly explains what kind of data we use to combine together. The data is complementary, but it can be quite simple at times to combine certain data types together. But in general, the algorithms can be quite complex. One of the more complex ones actually minimizes an error function to find an optimal balance between complementary data sets. This is specifically an NWP field and data from weather stations. I appreciate that's fairly esoteric, but you can get a sense of how complex things can get. Now, the thing I would like to talk about now is the radar data that we use. It's radar data, weather radar, which you've seen on TV and certainly on weather apps, our weather apps, and internet websites. It's certainly the preferred data set for detecting rain or snow, but there simply aren't enough weather radars to cover all of the geographies around the world. Excuse me. The best networks are in North America and Europe, but we also need information elsewhere because we provide data globally. And most parts of the Earth's surface do not have enough weather radar coverage. So in the future, what we plan to do actually is to, we already fill the gaps by merging weather radar with other data sets inside virtual observations, but in the future, we think we can get the precipitation conditions, rain and snow, from weather satellites, and that's a new project that we're working on. We're going to use machine learning methods to convert the radiance data that the satellite measures into precipitation at the surface. That's still in research. Okay, so the next few hours after the current conditions, this shows you, this is really about nowcasting, what we call nowcasting. The name itself is a little bit unfortunate, but basically it means that it's heavily weighted towards observations. Precipitation nowcasts enable end users to get estimates of start and stop time or timing of precipitation. There are two main methods in general use. Extrapolation of radar echoes on the one hand and the use of NWP models on the other. Our algorithm actually combines both of these methods. So the time animation loop on the right-hand side is an example of what our algorithm does. You can see, I'll just point out a couple of things. There's rain over Michigan. As the loop progresses, it gets more organized and as it approaches southwest Ontario. And then the rain over southern Ontario decays as it approaches the GTA, if you watch the loop as it runs. Radar extrapolation could not capture those particular changes. Radar extrapolation simply takes a radar image and moves it across the landscape. This is doing much more than that. It's actually predicting the growth and decay of precipitation. Unfortunately, though, we can't use NWP alone. It sort of sounds like NWP is a better data set to use, but in reality, it's not. And the reason is on the chart on the left-hand side. You can see in the chart that radar extrapolation actually starts with much better skill in the very first few hours, but the skill deteriorates rapidly. The blue line is a representation of what NWP skill would look like, and it starts at a lower level, but it tends to be relatively flat, improving beyond radar extrapolation in the longer term. So what our solution does, roughly speaking, is mirrors the green line in terms of skill. Weather forecast accuracy always decreases as the lead time increases, as you go further out into time. But what we did with Nowcasting was find an optimal balance between the two approaches. It was actually quite a complicated project and remains so from a support point of view. Okay. Statistical forecasts. I mentioned earlier that we make heavy use of NWP data. There are many individual NWP forecasts. So if I start on the left-hand side of the slide, and these many individual forecasts have to be combined into one consensus forecast. The consensus forecast is really just a blend of all of the individual forecasts, and it's usually more accurate than any of the individual forecasts themselves. Basically, I think in this particular case, it's fairly safe to say that the concept, at least anyway, is that the whole is greater than the sum of the parts. The problem is probably, well, one way to visualize the problem is on the right-hand side. There's a chart there which shows for one location, the number of forecasts available at a particular time. These happen to be minimum temperature forecasts for a location in Spain earlier this year. And the colored dots are individual forecasts generated at different times, all valid at the same time, 12th of January. The black horizontal line was the observation -8 degrees Celsius, and the consensus forecast, which was a blend of all of the individual forecasts, came out to be -7.6 something. So the error in the consensus forecast was only about 0.5 degree Celsius or less. The error in the individual forecast would have been significantly greater. You can see that with an observation of -8, some of the forecasts were predicting around +2. So significant errors if you just rely on the individual forecast. This is why we use consensus forecasts. So what we do is we continually measure the accuracy of the system that produces these consensus or statistical forecasts. And the charts show for temperature and wind speed the results in September of this year. These are averaged across about 6,000 locations globally. The red line is basically the average error from the individual forecasts, and the blue line is the error from the consensus forecast. Lower error being better. The blue line actually demonstrates that the consensus forecast concept works quite well. These charts, I'm just showing 1 month, September 2020, but if I were to go back over 2 or 3 years, I could generate similar charts with similar results. In other words, it's consistently better than the individual. The consensus forecast is consistently better than the individual input forecasts. Okay. Location-based forecasts. The keystone of our weather product suite is location-based forecasting. It really always has been. This is largely because weather can vary significantly in time and space. So we can provide a forecast for some city, but if you're located nowhere near that city, the forecast that you get won't be representative for your particular location. So that's why we place a high priority and emphasis on location-based forecasting. It surprises some people, but weather can change significantly within a distance of 1 kilometer or less. This is particularly so where you have land and sea boundaries, and especially in mountainous regions where we have complex terrain. you need to be able to represent local effects. So much of our data is represented on a 2D grid or two-dimensional array, and we start with a relatively coarse grid, such as the yellow one you can see on the map there, and then we convert this to a much higher resolution, I would say, grid or more local information. You can see by perhaps the red grid cells, the small red grid cells in Toronto there. We chose 1 kilometer as the target resolution. We could actually go higher resolution than if we wanted to. We could use the same algorithm to get down to a much better resolution. But we've basically settled on 1 kilometer as a reasonable local forecast for most people. The elevation of your location is critically important to this. We designed an algorithm which enables us to take into account changes in elevation between, let's say, the yellow grid and the red, to try to model these changes in the weather due to elevation. It's probably the single biggest control on weather, actually. It's not uncommon in dry climates to find 10 degrees C differences in 1 kilometer vertically. For example, we found this I think it was in the Andes in Chile, actually. The localization method that we use, it was designed several years ago, applied to North America, and right now we have a project underway to expand it to other parts of the world. Okay, this wasn't on the agenda, but I wanted to cover it anyway, just forecasting for long term. Seasonal and sub-seasonal forecasts. By sub-seasonal, we mean things like monthly forecasts or perhaps forecasts of several weeks duration. These are all firmly based on an assessment of the ocean conditions. The ocean stores an awful lot of heat. I think about 90% of the heat in the climate system ends up there, and it basically dictates a lot of the structure, location, and behavior of large climate components such as El Nino. There are numerous data sources used to produce these sub-seasonal and seasonal forecasts. They're basically models a lot of the time, much more complicated versions of NWP, but they're combined together as well, usually by expert judgment to come up with the sub-seasonal or monthly and seasonal forecasts. And in recent years, there's actually been an exponential increase in the number of products and services for the longer time ranges. And these longer time scales are actually the next frontier in weather information services that we're expecting to happen. And our job in R&D is basically to keep moving forward on these pathways so that we can improve weather information for all of our customers. Thanks, everyone.